Okay, Assalamu alaikum. We are Group 9, and today we will present our project in design and optimization of 128.50 using high-level synthesis. In this presentation, we will explain our project, the implementation process, the optimization techniques, and the final result. Uh, Next. Okay. So this is our presentation agenda. First, I will introduce the project background, problem statement, objectives, methodology, and the first implementation steps. Then my teammates will explain baseline implementation and the first optimization. And here, first, let's explain what FFT is. FFT stands for the fast Fourier transform. It converts a signal from the time domain into the frequency domain. This helps us to analyze the frequency inside a signal. FFT is widely used in communication system, radar, and audio, and image processing. However, software implementation may not be fast enough for real-time systems. To improve performance, we use high-level synthesis or HLS. HLS converts to C or C++ into FPGA hardware automatically, making hardware development easier and faster. The main problem is that simply converting C++ code into hardware doesn't always produce the best design. We want to find which optimization techniques improve performance while keeping the hardware resources efficient. So here in the objectives, we have four objectives. First, create Python benchmark for a 128 points FFT. Second, we implement the same FFT in Vitis HLS and verify its correctness. And third, we analyze baseline design by measuring timing, latency, power, and hardware resources. And finally, to apply two optimization methods and compare them with the baseline design. In the methodology, these slides show our complete workflow. We start by creating the FFT benchmark in Python. Next, we implement the 128 points FFT in Vitis HLS. Then we perform synthesis, C synthesis. After that, we verify the design using C simulation and RTL co-simulation. Finally, we implement the design in Vivado to obtain timing power and resources utilization. The same processes is repeated for both optimization versions. Here in the tools, these are the tools we use in our project, Python and NumPy and Matplotlib. Used to generate the test signal and benchmark the FFT. And finally, G++ was used for software verification. And our target FPGA was the Kintex Ultra Scale Plus with a target clock period of 10 nanoseconds. Wait. Okay. The input signal design for testing, we're generating 128 sample sine wave. The signal frequency is 10 megahertz, while the sampling frequency is 256 megahertz. This places the signal exactly on FFT bin number 5. As a result, we obtain a clean spectrum without spectral leakage or and making it idle for verification. Python benchmark result. After running the FFT Python, we obtained a clean single peak in the frequency domain. The average execution time was approximately 0.006 milliseconds. The output was saved as the golden reference and later used to verify both the C++ and HLS implementation. And for this slide, the original design was a 4-point FFT to scale 120.8, we only changed the site definition from 4 to 128, updated to the number of FFT stages. The main FFT algorithm did not need modification because it was already written in a generic way. And in this slide, finally, we perform C simulation in Vitis HLS, and as you see, this is the result here. And now we'll move to Ali. He'll explain the next slides.
All right, thank you, Nasser. Now I will present the baseline implementation results. After verifying the FFT design, we performed C synthesis using Vitis HLS. The estimated clock period has around 7.264 nanoseconds, which is better than our target of 10 nanoseconds. The synthesis also reported the FPGA resource usage, including DSPs, flip-flops, LUTs, and BRAM. These results showed that our design could successfully meet the time. Okay, so for this slide, as you can see here, we performed the CRTL co-simulation. The simulation passed successfully, meaning the RTL hardware produced exactly the same output as the C test bench. The total latency was exactly 7,359 clock cycles, and this is the final and accurate latency value for the baseline design. Next, please. So after what we did, we imported the design into Vivado. Vivado generated the actual FPGA resource utilization, although the resource numbers changed slightly compared with the HLS estimation, the DSP usage remained the same. And this also confirms that our HLS estimation was accurate. Next, please. Okay, so place and route. So that's the next step. We have both processes completed successfully without any errors. As you can see, this means the design could be successfully mapped onto the FPGA and all connections are routed correctly. Next. So as you can see here, we have our final implementation results. All timing constraints were successfully met. The total power consumption was about 0.523 watts, including both dynamic and static power. The FPGA utilization was also relatively low, using only a small percentage of LUTs, flip-flops, and DSP blocks. So overall, the baseline implementation was successful, as you can see. Next, please. So here we applied our first optimization A. So instead of calculating cosine and sine values during execution, we stored them in lookup tables. The hardware simply reads the required values from memory. This reduces the amount of computation because memory access is much faster than repeatedly calculating the functions, the amount of additional memory, please. Okay, so for this slide, after applying the lookup table optimization, we compared the results with the baseline design. The FFT output remained correct, while the hardware became more efficient because unnecessary calculations were removed. This optimization improved performance without affecting the accuracy of the FFT. Next, please. Our second optimization uses HLS performance pragmas. These are compiler directives that help Vitis HLS optimize loops and hardware execution automatically. The purpose is to increase parallelism, reduce latency, and improve throughput. And now my teammate Anas will take it from here. Thank you.
Okay, thank you. Now I'll continue with the results of optimization B. After applying the HLS performance pragmas, we observe an improvement in hardware performance. The design achieved low latency and a better throughput because more operations could be executed in parallel. However, the optimization also increased the use of FPGA resources. This shows the trade-off between higher performance and higher hardware utilization. Next, please. This slide compares the execution performance of all three designs. The baseline design provides the reference performance. Optimization A improves efficiency by replacing trigonometric calculation with lookup tables. Optimization B provides the best performance because it allows the hardware to execute more operations simultaneously. Next, please. Here we compare the FPGA resource usage. We can see that each optimization affects the hardware differently. Optimization A uses a small amount of extra memory for the lookup tables. Optimization B uses more FPGA resources due to the increased parallelism. Therefore, choosing the best design depends on whether performance or resource efficiency is the priority. Okay, this slide summarizes the timing and powering results. All three implementations successfully met the required timing constraints. The power consumption remained relatively low for each design. Overall, the optimization improved performance while maintaining an acceptable power consumption. From our comparison, we can see that each design has its own disadvantage. The baseline design is simple and uses fewer resources. Optimization A reduces unnecessary calculations with only small hardware cost. Optimization B provides the highest performance but requires more FPGA resources. This demonstrates the importance of the selection of the right optimization technique based on the application requirements. To conclude, we successfully implement 128 FFT using high-level synthesis. We verify the design using Python C simulation, RTL co-simulation, and FPGA implementation. Both optimization methods improve the overall design while maintaining correct FFT functionality. Next, please. This brings us to the end of our presentation. Thank you very much for your attention. We hope you found our presentation informative. We are happy to. Thank you.